Hi, welcome to my video on impulse and momentum. As warned previously, this will be pretty similar to what we went over in lab last week. So the main thing that we start with is we need our definition of momentum. So momentum is equal to mass times velocity. So momentum gets the lowercase p. I don't remember the origins of that at the moment, but m's already used for mass, so we can't use m for it. So momentum is equal to mass times velocity, remembering that the velocity is a vector, so therefore momentum is going to be a vector. If we look back at Newton's second law, we had F equals ma. But if we use the definition that the acceleration is the derivative of velocity with respect to time, that gives us m dv dt. But as we've been talking about, mass is a constant, so that's where we can bring that inside. We're just putting mass inside of there. And that is what we've just called the definition of momentum. So dp dt. And going across to the left, we have that all that's equal to the force. So this is a different way of thinking about Newton's second law, where the net force on an object is going to change its momentum. The net force is going to be the change in momentum and the change in time. So this is a different but equivalent way of thinking about the Newton's second law. And technically, if I'm trying to be perfect and 100% precise, all of those should be vectors. And we're talking about the net force. Now, if we're going to just think about one dimension for now, because as we've been doing in the past, we start in one dimension and we'll work our way up into multiple dimensions. So starting with one dimension, that's where we have dp dt equals f. And we'll think about just one force. So the differential change in momentum over the differential change in time is equal to the force acting on the object. But I'm just going to multiply both sides by dt so that we have the differential change in momentum is equal to the force times the differential change in time. So in a very small, if a force is applied for a very small amount in time, we'll have a very small change in momentum. But we can integrate both sides of this, and that will make the right side of the equation, since there's just the integral of dp, it'll just be our change in momentum. But for an arbitrary force like I'm talking about right now, we can't say anything about the right side of the equation. And this here is the momentum principle, where the change in momentum is going to be equal to the sum of the force the integral of force with respect to time, which is essentially saying at each small chunk in time, the force will be applied and give us differential change in momentum. If we add up all those little differential changes in momentum, we get the total change in momentum. And the idea behind this is called impulse. And more often than not, the integral part is what's referred to explicitly as the impulse. So this is the base definition of impulse and momentum. And if we're going through and doing vectors, we can put the vectors back in where the p, and then it'll be the integral of force dt. And noting that the force can possibly change directions and times. Now, if we have a constant force, that's where we can say the change in momentum is going to be equal to the force. So the force is constant and now it's the integral dt. So that's where we would get force times the change in time. So another case of constant force, we'll get this simpler form, and this will be often used. And again, I could put vectors on all those to talk about it generally. So then the thing to remember is that because we're talking about this way of integrating the force over time, we've seen a few examples of this now. If we have force and time, and we wanted to figure out what the change in momentum area under the curve would be, the change in momentum. And I guess the last thing that I want to sit and comment on is that the units, so it would be a Newton times a second, which if we think about that, that's kilogram meter per second squared second. So it cancels out. So kilogram meter per second, which we would, expect from the fact that it's the mass times the velocity. So mass meters squared doesn't have a special name, just kilogram meters per second. So that's the base idea behind it, and then it's a lot of application. One of the big reasons we'll end up using impulse and momentum now is when we talked about energy, we were skipping time, ignoring the time. Now with impulse and momentum, we can solve problems using the momentum principle and the impulse. So another way of sort of skirting around kinematics and complex forces to figure out changes and things. All right. Hopefully that helps.